Hello and welcome to The Sleepy Scientist, your cozy corner of the cosmos, where we explore the wonders of science in a way that's soothing, fascinating, and just relaxing enough to gently lull you toward dreamland. Tonight, we're setting out on an extraordinary journey, the story of our home, planet Earth. From molten beginnings and deep oceans teeming with ancient microbes, to lush forests, roaming dinosaurs, and eventually the rise of curious creatures like us. It's a story over 4 billion years in the making, and we're going to drift through it one calm breath at a time. Now, I should warn you, this video may contain facts so interesting they risk keeping you awake. If that happens, well, at least you'll be wide-eyed and wonderfully informed. But ideally, the soft rhythm of the story will help you float peacefully into sleep. Before we begin, if you enjoy these gentle dives into science and nature, please consider giving this video a like and subscribing to the channel. It helps more sleepy minds discover our little pocket of quiet curiosity. And if you're feeling extra cozy, let me know in the comments where in the world you're listening from and what time it is as you hit play. There's something lovely about knowing we're all drifting together, even if we're oceans apart. Now, as always, a gentle reminder: while we talk about biology, evolution, time, and the occasional cosmic accident, nothing here is medical advice, psychological guidance, or a substitute for professional care. This is simply a peaceful place to learn something new and maybe fall asleep along the way. Alright, if you're ready, take a slow breath, let it out, and let's begin our journey through the history of planet Earth. Long before mountains rose and oceans shimmered blue, before trees shaded the ground or birds filled the sky with song, before Earth even existed, there was dust. Not the kind you sweep under a rug, but cosmic dust, the ashes of ancient stars scattered across the vast dark canvas of space, and in that dust lay the beginnings of everything. You, me, the oceans, the clouds, the crusty surface of a good pizza. It all started with stardust. Let's set the scene. The universe began around 13.8 billion years ago, with the event we call the Big Bang. Now, despite the name, it wasn't so much a bang in the noisy sense, as it was an abrupt expansion of space itself. No fireworks, no dramatic soundtrack, just a sudden, silent unfolding of time, matter and energy, from a single, infinitely dense point. In those first few moments, things were toasty, unfathomably hot, too hot for atoms or anything even remotely resembling matter. But as the universe expanded, it cooled, like a cosmic cup of tea left out too long. And as it cooled, the very first elements began to form, mostly hydrogen, a bit of helium, and trace amounts of lithium. Not much to write home about in terms of a chemical buffet, but it was a start. These simple gases began to gather into enormous clouds, drawn together by the quiet, persistent tug of gravity. Over millions of years, the clouds collapsed under their own weight, squeezing atoms so tightly that nuclear fusion ignited at their cores. And just like that, the first stars were born. These first-generation stars were immense, short-lived giants. They burned brightly, lived fast, and died young, often in spectacular explosions called supernovae. These were not gentle affairs. A supernova releases more energy in a few seconds than our sun will emit in its entire lifetime. But out of that violence came beauty. Inside those dying stars and during their explosive ends, heavier elements were forged. Carbon, oxygen, iron, and all the other building blocks that life and planets require. So when we say we're made of stardust, we're not being poetic. We're being literal. The calcium in your bones, the iron in your blood, the oxygen you breathe, it all came from stars that lived and died long before our solar system even existed. Now fast forward a few billion years. A quiet region of our galaxy, the Milky Way, is filled with clouds of gas and dust enriched by those long-gone stars. Around 4.6 billion years ago, one of these clouds began to collapse. Perhaps it was nudged by the shockwave of a nearby supernova. Whatever the trigger, the cloud gave in to gravity and started to swirl. This spinning cloud flattened into a disk, like pizza dough tossed by an enthusiastic but inexperienced chef. At the centre of the disk, most of the material gathered to form a new star, our Sun. Further out, bits of rock and metal and ice clumped together, colliding and sticking, growing larger and larger over millions of years. These clumps would become planets, and one of them, about 150 million kilometres from the newborn Sun, was destined to become Earth. But let's not get ahead of ourselves. Earth didn't begin as the lush blue and green marble we know today. In the beginning, it was a chaotic, violent construction site in the cold vacuum of space. In its earliest days, Earth was still forming from countless collisions with other space debris. Imagine a sphere of molten rock being pelted by everything from pebbles to planet-sized objects. One of these collisions was especially important. A Mars-sized body we call Theia slammed into the young Earth. The impact was so enormous that it vaporized much of Earth's outer layer and flung debris into orbit. Over time, that debris coalesced into our Moon. This dramatic event reshaped Earth. It tilted the planet's axis, which gave us seasons. It also helped stabilize Earth's rotation, making conditions more favorable for life, though that would take a while to show up. For now, Earth was a molten hellscape, with a surface temperature hot enough to melt iron, and a sky choked with volcanic gases. But Earth was cooling. Slowly over millions of years, the surface began to harden. A crust formed. Volcanoes spewed gases like water vapour, carbon dioxide and ammonia into the atmosphere. There was no oxygen yet, no breathable air. The atmosphere was thick, toxic and heavy, but it was the beginning of weather, of clouds, of rain. Where did the water come from? That's still debated, but two main theories float around, so to speak. One suggests that water was part of Earth from the start, released by volcanic activity. Another proposes that icy comets and water-rich asteroids delivered it after Earth cooled. The truth may lie somewhere in between. Either way, over time, enough water gathered on the surface to form oceans. Rain fell on lava plains. Lightning flashed over churning seas. Meteorites continued to bombard the young world, though less frequently than before. Earth was still inhospitable by human standards, but it was beginning to take shape. Beneath the crust, Earth's interior remained active. The planet's core, made mostly of iron and nickel, began to spin. This movement created Earth's magnetic field, which would one day protect the planet from solar radiation. Above, the atmosphere thickened, trapping heat and enabling liquid water to remain stable on the surface. And then, after hundreds of millions of years of geological and chemical chaos, something truly remarkable began to happen. Tiny organic molecules formed in Earth's oceans. These were not yet alive, but they were the precursors to life, the building blocks of biology. Perhaps they assembled around mineral-rich hydrothermal vents deep beneath the sea, shielded from the harsh surface conditions above. The stage was now set for the origin of life, but that's another chapter in Earth's long, winding story. For now, as we float in the calm of this moment, it's worth reflecting on just how lucky we are. Our planet formed from stardust, survived violent impacts, cooled just enough to hold oceans, and spun under the warmth of a steady sun. It sits in just the right spot in our solar system, not too close, not too far, to allow for liquid water. Not too hot, not too cold. It is, in the most literal sense, a Goldilocks planet. And while Earth may seem enormous to us, it is just one rocky world among billions in our galaxy, spinning silently, steadily, through space. So the next time you feel small, remember, you're the product of a grand cosmic history, a tale that began in the hearts of ancient stars, carried through time on the winds of gravity and chance, and came to rest for now, here, on this pale blue dot we call home. Let your thoughts settle with the dust of the universe. Let your breathing slow. as the stars above once slowed to form the very matter that now makes you. And as Earth turns quietly beneath the moonlight outside your window, know that you are part of something vast, ancient, and deeply beautiful. The Earth you know, the one with blue oceans and fluffy clouds, rustling trees and cozy thunderstorms, didn't always look this way. In fact, if you had taken a little stroll across the surface of early Earth, say around 4.5 billion years ago, you wouldn't have lasted very long. Not because of saber-toothed cats or volcanic eruptions, although those would come later, but because the surface was more or less a bubbling ocean of lava. Not ideal for picnics or morning walks. This was the Hadean Eon, named after Hades, the Greek god of the underworld, which gives you a fairly accurate idea of the general ambience. Earth had only just formed, a process known as accretion, where dust and rock in the solar system gradually clump together under gravity's persistent tug. And when we say clumped, think less soft snowballs and more high-speed space rock collisions. Each impact released massive amounts of energy, keeping Earth's surface in a molten, semi-liquid state for millions of years. The early solar system was a chaotic neighbourhood. Imagine rocks the size of small countries flying through space and crashing into one another like cosmic bumper cars. The Earth's formation wasn't a peaceful event, it was more like construction in the middle of a meteor shower. Every impact added to the planet's mass, but also released tremendous heat, preventing the surface from solidifying for quite some time. Now, during this fiery period, Earth was undergoing internal changes as well. Heavy elements like iron and nickel sank toward the centre, forming the core. Lighter materials floated upward, forming the mantle and eventually the crust. This process, known as planetary differentiation, gave Earth its layered structure: a solid inner core, a molten outer core, a viscous mantle, and a thin, brittle crust on top, sort of like a cosmic truffle, if truffles were full of magma. One particularly dramatic event during this time shaped not only Earth's future, but the entire rhythm of life that would eventually arise here: the formation of the Moon. According to the most widely accepted theory, a Mars-sized body, nicknamed Theia, collided with the young Earth. It wasn't a glancing blow. This was a full-force, high-speed impact. The collision vaporized much of Earth's outer layers and sent a vast plume of debris into orbit. That debris eventually coalesced to form the Moon. This explains why the Moon's composition is so similar to Earth's outer crust. But the Moon didn't just give us pretty night skies and occasional werewolf myths. It stabilized Earth's rotation. Without it, our planet would wobble unpredictably on its axis, creating wild climate swings that would have made the emergence of complex life far more difficult. The Moon also slowed down Earth's rotation over time. In the early days, one full spin of the Earth took only about 6 hours. So if you thought your workday was short now, imagine squeezing morning coffee, lunch and dinner into a single afternoon. After the impact and the settling of debris, Earth continued to cool. The surface began to solidify into crust, though not the kind of crust you might comfortably walk on. It was fragile, unstable, and frequently broken by volcanic eruptions. Beneath the crust, the mantle remained restless, churning slowly with heat from radioactive decay and the residual energy of formation. This internal heat engine would power geological activity for billions of years to come. As the planet cooled, gases trapped in the molten rock began to escape through volcanic activity. These gases, mostly water vapor, carbon dioxide, nitrogen, and small amounts of methane and ammonia, rose into the sky and formed Earth's first atmosphere. Notably absent from this early brew was oxygen. The air, if you could call it that, was toxic to anything that might someday need to breathe. Still, the atmosphere served an important purpose. It trapped heat, moderated temperature swings, and set the stage for the next major transformation, the formation of liquid water. There's some debate about where Earth's water came from. One possibility is that water was already present in the materials that formed the planet and was released slowly through volcanic outgassing. Another theory suggests that water was delivered by icy comets, or water-rich asteroids during a period known as the Late Heavy Bombardment, an era that occurred around 4 billion years ago when the solar system was still a bit rowdy and collisions were common. Regardless of its origin, once enough water vapour accumulated in the atmosphere and the planet cooled sufficiently, rain began to fall, and fall, and fall. For centuries, millennia, perhaps even millions of years, the sky poured water onto the still warm crust. It hissed against hot rock, pooled in craters, and eventually gathered into the first oceans. Picture that. A scorched planet steaming beneath endless rain. Lightning crackling across thick clouds, and oceans slowly swelling in the lowlands of a young, restless world. It wasn't peaceful, but it was transformative. By around 3.8 billion years ago, Earth likely had significant bodies of water. These early oceans were not as blue as they are today. They were likely a murky mix, rich in dissolved minerals and metals leached from the crust. But they were crucial. Water is a universal solvent. It allows molecules to mix, interact, and form more complex structures. In many ways, water was Earth's first great laboratory. Meanwhile, tectonic activity had begun beneath the surface. The crust was thin and constantly shifting, driven by the heat below. This movement created the first proto-continents, small land masses that would eventually drift, collide, and grow into the continents we know today. The theory of plate tectonics, which explains this movement, wouldn't be fully understood until the 20th century, but its slow choreography began billions of years earlier. Volcanoes erupted often, not only on land but under the ocean as well. These underwater volcanoes formed hydrothermal vents, fissures in the seafloor that spewed mineral-rich, superheated water into the surrounding ocean. Around these vents, despite the extreme conditions, a surprising thing occurred. Complex organic molecules began to form. The ingredients for life, carbon compounds, simple amino acids, and nucleotides, may have originated in these environments. These weren't yet living organisms, but they were the building blocks of life's chemistry. Earth had gone from a lifeless rock to a dynamic world with oceans, atmosphere, and rich supply of chemical ingredients. Life, in some small and primitive way, was waiting just around the corner. It's also around this time that Earth's magnetic field became more robust. Generated by the spinning iron core, this invisible shield protected the planet from the worst of the sun's radiation. Without it, solar winds could have stripped away the atmosphere, turning Earth into a barren husk like Mars. But with the magnetic field in place, and an atmosphere thick enough to hold heat and moisture, Earth became a protected bubble in an otherwise hostile solar system. The stage was set. Earth had a stable orbit around a reliable star. It had liquid water, volcanic activity, and a magnetic field. It even had a giant companion in the sky, pulling gently on its tides and stabilizing its spin. Everything was ready. Of course, life didn't appear overnight. The transition from chemistry to biology would take time, and the path would not be straightforward. But none of that would have been possible without this early, violent, and deeply transformative chapter in our planet's history. So, as you lie there, eyes gently closing, picture the young Earth. Molten rivers of lava cooling under an endless storm, meteors streaking across the sky, oceans forming in great crashing waves, volcanoes painting the horizon with ash and fire. It was wild, it was dangerous, and it was essential. Because sometimes it takes a little chaos to set the stage for beauty. The Earth had cooled, the crust had formed, oceans shimmered beneath cloudy skies, volcanoes still erupted here and there, puffing out steam and gas like ancient tea kettles. But things had calmed considerably compared to the planet's earliest days. It was no longer the scorched underworld of the Hadean Eon. Earth was, at long last, settling into a more stable routine. And in this newfound calm, something wonderful began to stir. Water, weather, and the delicate conditions that made life possible. Now, it's important to appreciate just how special water is. It's not just something you drink or splash around in on hot days, it's the great enabler. Water dissolves, transports, and transforms. It softens hard rock, it shapes coastlines, it's the backstage technician of life, quietly getting things done. But Earth's early water wasn't quite the crystal clear variety that tumbles from your tap today. The first oceans were rich in dissolved minerals and metals, leached from the crust by rain and hydrothermal activity. They may have been slightly acidic and tinged with hues of green or brown depending on the local chemistry. Still, there they were, vast stretches of liquid surface covering much of the planet, shifting and sloshing under the pull of the moon. It was in these ancient waters that Earth's weather systems were born. You might think of weather as something driven by clouds and pressure systems on your phone's forecast app, but at its heart, weather is just energy being redistributed. The sun shines down unevenly across the globe, warming some regions more than others. Warm air rises, cool air sinks, and this constant juggling act creates wind, rain, and climate. Even billions of years ago, Earth's spinning motion and axial tilt gave it patterns. Sunlight heated the equator more than the poles, creating circulation in the atmosphere. Ocean currents began to flow. Clouds formed. Rain fell. And somewhere, perhaps for the very first time, a rainbow might have arced across the sky. These early weather systems helped shape the land. Rain wore down rocks, carving out channels and valleys. Rivers began to form, meandering slowly toward the sea. Sediments were carried and deposited layer by layer, laying the groundwork for future continents and ecosystems. In a way, weather was the planet's first artist, slowly sculpting its surface with wind, water, and time. And while the atmosphere still wasn't breathable for creatures like us, it was changing. Volcanic gases continued to pour into the air, thick with carbon dioxide, water vapour, ammonia, and methane. There was no oxygen yet, at least not the free-floating kind. But deep beneath the waves, invisible to the eye, something extraordinary was happening. Tiny organisms, simple single-celled bacteria, had emerged. Exactly how life began is still one of the great scientific mysteries. Some researchers believe life may have started around hydrothermal vents at the bottom of the ocean, where mineral-rich superheated water pours from the seafloor. Others suggest shallow tide pools, where sunlight, evaporation, and chemical reactions could have kick-started the first biological processes. Either way, by around 3.8 billion years ago, life had appeared. These earliest microbes were humble little things. No legs, no eyes, no grand ambitions. They simply floated, absorbed nutrients, and occasionally replicated themselves. But they were alive, and they were astonishing. These primitive organisms belong to the domain of life we call prokaryotes. That means they didn't have a nucleus or complex internal structures. They were more like self-replicating bubbles of chemistry. Yet despite their simplicity, they were incredibly resilient. They adapted to extreme environments, including boiling vents, acidic waters, and areas with no sunlight. Some of these early microbes developed a particularly game-changing talent: photosynthesis. Now, modern photosynthesis is the process by which plants, algae, and certain bacteria use sunlight to convert carbon dioxide and water into glucose and oxygen. But the earliest photosynthesizers didn't make oxygen, at least not at first. They may have used other molecules like hydrogen sulfide to produce energy. Eventually, though, some clever bacteria developed a version of photosynthesis that did release oxygen as a byproduct, and this changed everything. These bacteria, called cyanobacteria, were the first organisms to truly make use of sunlight in the way that modern plants do. Floating in shallow seas, they formed slimy colonies that grew into structures known as stromatolites. These layered mounds, still found in a few places today, are among the oldest visible fossils on Earth. As cyanobacteria flourished, they began to pump oxygen into the oceans. At first, this oxygen reacted with dissolved iron, forming rust that settled onto the seafloor. This gave rise to what we now call banded iron formations, beautiful striped layers of rock that mark the ancient oxidation of the seas. For millions of years, the oceans turned reddish-brown with rust before finally becoming saturated. And then, something dramatic happened. Once the iron in the oceans was used up, the oxygen produced by cyanobacteria began to escape into the atmosphere. This slow accumulation of oxygen, starting around 2.5 billion years ago, ushered in what scientists call the Great Oxidation Event. But we're getting ahead of ourselves just a bit. Back in our watery world of 3.5 billion years ago, Earth was still a planet of extremes. The land was mostly barren rock, possibly dotted with volcanic islands and small proto-continents. Lightning still cracked across stormy skies. The air was thick with greenhouse gases, and the sun shone fainter than it does today. In fact, the young sun was about 30% less luminous than it is now. You might think that would plunge Earth into a deep freeze, but greenhouse gases like carbon dioxide and methane helped trap enough heat to keep the planet warm. This delicate balance between atmospheric gases, solar energy, and oceanic chemistry kept Earth in a narrow range of temperatures that allowed liquid water and life to persist. It wasn't perfect, but it was enough. And in the quiet shallows of these primeval oceans, biology slowly tinkered, adapted, and evolved. Cells learned to divide more efficiently. Some may have started sharing genes. Simple communities began to form. Microbial mats blanketed the seafloor, catching sunlight and releasing waste products that would eventually reshape the entire planet. Meanwhile, tectonic forces continued to move the crust. Plates collided and drifted, raising mountains, deepening basins, and giving the planet its first sense of geography. New volcanic islands sprouted, old ones sank, and with every shift in the land, new habitats appeared, offering fresh opportunities for life to diversify. But Earth's development wasn't a straight line. There were setbacks, massive impacts, eruptions and climate swings that tested the resilience of life at every turn. And yet, something always endured. Some humble little microbe would survive the storm, multiply, and carry the flame of life forward. And that's the quiet magic of this chapter in Earth's history. There were no dinosaurs yet, no forests, no mammals curled in cozy burrows. But the groundwork was being laid. The oceans were stirring with possibility. The skies were beginning to shift. The chemistry of life was rehearsing, refining, and preparing for a grander stage. So if you're drifting off now, let your mind float gently above a world of ancient tides. Imagine a cloudy sky over a restless sea. Picture tiny, unseen organisms working tirelessly in warm shallows, weaving the very fabric of life beneath the waves. In this watery, weathered world, life had begun, and the planet, shaped by wind and water, was just getting started. Somewhere in the warm shallows of an ancient ocean, beneath skies choked with volcanic haze and clouds, heavy with the memory of 1,000 storms, life found its spark. It was quiet. No trumpet fanfare, no flash of lightning announcing its arrival, just molecules bumping into each other, linking up, and, at some point, crossing the almost magical threshold between chemistry and biology. We don't know exactly when it happened, or even precisely how, but it did. At least once, and possibly many times on the young Earth, simple organic molecules assembled into self-replicating structures. These humble, microscopic bundles would become the ancestors of everything. Trees, whales, mushrooms, people, and even the moss that grows between the cracks in your garden path. The journey from lifeless molecules to living cells was long and mysterious, but it began here, in Earth's vast and ancient oceans. The earliest life was made up of incredibly simple cells known as prokaryotes, organisms without a nucleus or membrane-bound organelles. Think of them as the minimalists of the biological world. They were tiny, efficient, and perfectly suited for an environment that would have been toxic to anything more complex. They didn't need oxygen. In fact, they couldn't tolerate it, and many of them likely thrived in hot, acidic, or otherwise extreme conditions. One popular idea about where life may have begun centres around hydrothermal vents. These are cracks in the seafloor where geothermally heated water gushes out, often rich in minerals like iron and sulfur. These environments, known as black smokers and alkaline vents, still exist today and are teeming with microbial life. The combination of heat, minerals, and the natural energy gradients around these vents might have provided the perfect conditions for organic chemistry to come alive. Another possibility is that life began in shallower pools, warm, sunlit tide pools on volcanic islands, where evaporation could have concentrated molecules and sunlight could have powered early chemical reactions. In either case, the basic ingredients were available: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all the essential building blocks of life, swirling and mixing in a planet-sized petri dish. Eventually, through trial, error, and an immense passage of time, some of these primitive molecules began to replicate. This might have involved RNA, a molecule similar to DNA but simpler and more flexible. In modern cells, RNA helps read genetic instructions and build proteins, but in the earliest life forms, RNA may have done it all, storing information, catalyzing reactions, and even copying itself. Once replication began, evolution could take hold. Mistakes in copying created variation. Some variations were more stable or more efficient, and those versions were more likely to persist. Slowly, over millions of years, molecules became protocells, simple, membrane-bound structures capable of metabolism and reproduction. Life had arrived, not in a single miraculous leap, but in a slow, meandering stumble toward complexity. These first cells fed on the chemicals around them. Some absorbed simple molecules from their environment. Others may have harvested energy from sunlight or inorganic compounds like hydrogen sulfide. They formed dense mats on the seafloor and in shallow lagoons, clinging to rocks and surfaces where nutrients were plentiful. These microbial mats were Earth's first ecosystems, tiny, slimy, and surprisingly resilient. By around 3.7 billion years ago, we begin to find evidence of life in the geological record. Ancient rocks from places like Greenland and Western Australia contain isotopic signatures, subtle chemical fingerprints that suggest biological activity. There are also microfossils and stromatolites, which are layered structures built by colonies of microbes, particularly cyanobacteria. These living fossils still exist today in a few places, like Shark Bay in Western Australia, where the saltiest slated waters preserve a glimpse of the ancient past. Cyanobacteria were a game changer. They developed a form of photosynthesis that used sunlight to split water molecules, releasing oxygen as a byproduct. This was a radical development. Before cyanobacteria, photosynthesis may have used other chemicals like hydrogen sulfide, but oxygen-producing photosynthesis was something new, and it would end up transforming the entire planet. At first, the oxygen produced by cyanobacteria didn't accumulate in the atmosphere. Instead, it reacted with dissolved iron in the oceans, creating rust that settled on the seafloor. This process continued for hundreds of millions of years, forming thick bands of iron-rich rock that we now mine for steel. These banded iron formations are some of the clearest geological evidence of Earth's early microbial life. But eventually the ocean's iron ran out. There was nothing left to bind the oxygen, so it began to seep into the atmosphere. This slow but steady increase in atmospheric oxygen led to one of the most significant events in Earth's history, the Great Oxidation event, which occurred around 2.4 billion years ago. For the microbes that had evolved in an oxygen-free world, this was bad news. Oxygen is reactive. It damages delicate biological molecules and can be deadly to organisms that aren't equipped to handle it. In fact, the rise of oxygen caused a massive extinction event, an invisible cataclysm that wiped out countless anaerobic species. But for others, it was an opportunity. With oxygen in the air, new forms of metabolism became possible. Cells could now extract far more energy from their food than ever before, using oxygen to efficiently burn carbohydrates and fats. This metabolic upgrade laid the groundwork for more complex life forms, but evolution wasn't in a rush. It would take another billion years or so before complex cells appeared. These are known as eukaryotes, organisms with internal compartments, including a nucleus to house their DNA. The leap from prokaryotes to eukaryotes was enormous, and likely involved one of the most remarkable acts of cooperation in biological history: endosymbiosis. According to the endosymbiotic theory, eukaryotic cells arose when one cell engulfed another, and instead of digesting it, decided to keep it around. The engulfed cell continued to live and function inside its host, eventually evolving into specialized organelles. Mitochondria, the powerhouses of modern cells, are believed to be descendants of ancient bacteria that once had their own independence. Likewise, chloroplasts, the structures that perform photosynthesis in plant cells, were probably once free-living cyanobacteria. This unlikely merger allowed cells to become larger, more complex, and more efficient. Eukaryotes could now store more DNA, build more proteins, and develop new structures like cilia and flagella to move around. Life was beginning to diversify in earnest. Still, for much of Earth's history, microbes remained the dominant form of life. Even with the arrival of eukaryotic cells, the planet's biosphere was mostly microscopic. Oceans teemed with plankton and bacteria, exchanging gases with the atmosphere, shaping the climate and continuing the slow work of evolution. Meanwhile, the Earth itself continued to change. Continents drifted, mountains rose, volcanoes erupted, and oceans shifted. The atmosphere thickened with oxygen, and the skies turned a familiar shade of blue. The moon continued to pull at the tides, and sunlight continued to pour down from above, steady, nurturing, and ancient. And in the quiet recesses of the sea, evolution kept experimenting. Cells started cooperating, forming simple colonies. Some began to specialize, one cell for movement, another for digestion, another for reproduction. These were the first steps toward multicellular life, a kind of cellular teamwork that would eventually lead to plants, animals, fungi, and everything in between. But those grand developments still lay ahead. For now, the Earth was a world of water and light, where life floated gently beneath the waves, drawing energy from the sun and minerals from the Earth. It was a planet teeming with potential, quietly waiting for its next great transformation. So as you settle in tonight, eyes growing heavy, imagine a world without cities or continents, just an endless ocean under a hazy sky. The surface dappled with sunlight, tiny cells drifting, dividing and evolving, unseen but unstoppable. A living world in its infancy, full of promise, gently spinning beneath the stars. Life had begun, and it would never look back. It's hard to overstate just how much oxygen has changed the world. Today we take it for granted. Every breath you take, every campfire, every rusting garden spade, it all involves oxygen quietly going about its business. But there was a time, deep in Earth past, when this colourless gas was rare, exotic, and even dangerous. In fact, its appearance marked one of the most dramatic turning points in our planet's history. You might call it Earth's first environmental crisis, although the cyanobacteria responsible would probably call it a job well done. Let's rewind to around 2.4 billion years ago. The planet had already been around for a couple of billion years. It had oceans, weather, continents starting to take shape, and microbial life bubbling away in all sorts of watery corners. But the atmosphere, that was still not exactly spa quality. There was no oxygen to speak of. Instead, the air was filled with volcanic gases, carbon dioxide, methane, ammonia, and other ingredients that would make today's environmental scientists break into a cold sweat. Then came photosynthesis. Not the kind we learn about in school with trees and flowers, but an earlier microbial version practiced by cyanobacteria These tiny blue-green organisms evolved a way to capture energy from sunlight and use it to split water molecules. The byproduct? Oxygen gas. At first, this oxygen didn't go very far. It was immediately mopped up by iron and other elements dissolved in the oceans. The result was a planetary cleanup effort on an epic scale. As oxygen bonded with iron, it created iron oxide, what we call rust, which fell to the seafloor and built up over time in thick, layered formations. These banded iron formations, still found in ancient rocks today, are a geological record of Earth's great rusting. This process went on for millions of years. Oxygen was produced, iron soaked it up, and the seas turned reddish-brown with rust. But eventually the sponge was saturated, the iron ran out, and the oxygen started to accumulate, first in the oceans and then slowly but surely in the atmosphere. This was the beginning of the Great Oxidation event, sometimes affectionately abbreviated as the GOE. It sounds friendly, like a music festival or a quaint holiday tradition, but it was anything but gentle. As oxygen levels climbed, it fundamentally altered the chemistry of Earth's atmosphere, oceans and biosphere. For many of the microbes that had evolved in a low-oxygen world, this was catastrophic. Oxygen is a highly reactive molecule. It's great for things like combustion and metabolism, but it can be toxic to cells that aren't equipped to handle it. It damages proteins, DNA, and other delicate structures. Without protective enzymes or antioxidants, oxygen is essentially cellular napalm. As a result, the Great Oxidation event triggered one of the first mass extinctions in Earth's history. Countless anaerobic organisms, those that thrived in oxygen-free environments, either died off or were forced into isolated pockets where oxygen could not reach. These so-called anoxic environments still exist today in deep-sea sediments, underground aquifers, and other oxygen-deprived nooks and crannies. They are like time capsules, holding relics of a long-lost microbial world. But as is often the case with mass extinctions, what's bad for some can be a golden opportunity for others. The rise of oxygen paved the way for entirely new biological strategies. With this new gas in the air and dissolved in water, organisms could now extract energy more efficiently from their food. Oxygen-based metabolism is roughly 16 times more effective than fermentation or other anaerobic processes. That's a massive energy boost, enough to support larger, more complex cells. And so, even as some forms of life were fading away, others began to thrive. Oxygen didn't just alter biology, it changed geology too. It helped stabilize Earth's climate by breaking down methane, a powerful greenhouse gas. This triggered a significant drop in global temperatures, so significant in fact, that it may have contributed to one of Earth's earliest and most dramatic ice ages. This frigid chapter is known as the Huronian glaciation. It occurred around 2.3 billion years ago, and may have lasted for hundreds of millions of years. Glaciers spread across much of the planet, possibly even reaching the equator. The world, once warm and stormy, was now cloaked in ice. Some scientists even think Earth may have been completely frozen over, a concept known as Snowball Earth. Now, Earth freezing solid might seem like a bit of an overreaction, but it's a striking example of how interconnected everything is. A single molecule, oxygen, produced by tiny bacteria, set off a chain reaction that altered the atmosphere, killed off a large portion of life and changed the planet's climate, all from microbes that had no idea they were rewriting the rules. Eventually, volcanic activity and the release of greenhouse gases like carbon dioxide warmed the planet again, melting the ice and returning Earth to a more temperate state. Life persisted. It always does. But the world it returned to was not the same. The air had changed, the oceans had changed, and the surviving organisms were slowly adapting to the new, oxygen-rich environment. Over the next several 100 million years, oxygen levels fluctuated. They rose, dipped, and rose again, influenced by geological events, biological feedback loops, and changes in Earth's carbon cycle. But the overall trend was clear. Oxygen was here to stay. One of the many gifts of oxygen was the formation of the ozone layer. High in the atmosphere, oxygen molecules began to absorb ultraviolet radiation from the sun. This process created ozone, molecules made of 3 oxygen atoms, which formed a thin but crucial shield around the planet. The ozone layer protected life from harmful UV rays, and made it safer for organisms to eventually venture out of the ocean and onto land. But that step wouldn't happen for a long time yet. Back in the oceans, life continued to evolve. The increased availability of oxygen supported the development of more energy-intensive cellular processes. Some microbes began living together in cooperative arrangements. These symbiotic partnerships eventually gave rise to the first eukaryotic cells, cells with internal compartments, including a nucleus. As we mentioned in the last chapter, these eukaryotic cells are thought to have evolved through endosymbiosis, one cell engulfing another and turning it into a permanent resident. This led to the creation of mitochondria, which handle energy production, and in some lineages chloroplasts, which perform photosynthesis. With more oxygen and more energy, the door to complexity creaked open. Cells grew larger, more structured, and more versatile. They developed new ways to move, sense their environment, and interact with each other. The genetic material stored in their nuclei allowed for greater regulation, more sophisticated communication, and the potential for specialized functions. We often think of the oxygen revolution as a single event, but in truth, it was a long, slow, and uneven process. Even after the Great Oxidation event, it took billions of years for oxygen levels to reach anything like modern concentrations. During much of this time, the oxygen levels in the atmosphere and oceans remained relatively low, only creeping upward in fits and starts. But it was enough. Enough for the first real steps toward multicellular life. Enough to give evolution a new set of tools. Enough to turn a quiet microbial world into a bustling, diversified ecosystem. So as you relax into your pillow, imagine the planet under a hazy, changing sky. Picture vast oceans swirling with microscopic life, each little cell busy converting sunlight into sugar and exhaling oxygen into the air. Imagine rusting seafloors, icy continents, and strange microbes eking out or living in dark corners where oxygen could not reach. This was Earth in transition, not yet the world we know, but no longer the one that came before. A planet learning how to breathe. And all of it, every glacier, every extinction, every cell division, began with sunlight, water, and the quiet, unseen labour of tiny organisms doing what they did best, staying alive. Earth is no stranger to extremes. It's been molten, radioactive, oxygen-deprived, and covered in volcanoes. But perhaps one of its most surprising disguises was when it tried out a rather dramatic new look, being almost entirely frozen. Yes, at one point in its long history, our warm, life-filled planet may have looked more like a giant cosmic snowball. Welcome to one of the chilliest chapters in Earth's story, the time of Snowball Earth. To understand how Earth went from warm and wet to icy and silent, we need to roll back the clock to around 700 million years ago. Life at this time still consisted mainly of simple organisms, algae, bacteria and other microbes, quietly floating in the oceans, soaking up sunlight and going about their microbial business. The atmosphere had slowly built up oxygen thanks to the efforts of cyanobacteria, and Earth was beginning to flirt with biological complexity. But then something changed. The climate began to cool, and not just a little. It wasn't the sort of cold that calls for an extra blanket or a cozy sweater. This was cold on a planetary scale. Glaciers crept from the poles toward the equator. Ocean ice spread far beyond the polar regions. In some models, ice may have reached all the way to the equator, encasing the planet in a shell of frozen silence. Scientists call this Snowball Earth, and while it sounds a bit whimsical, like something from a children's book, it was anything but cozy. The evidence for this event comes from strange rock formations called drop stones and glacial deposits found in places that are now tropical. These ancient clues suggest that, At one time, glaciers were grinding across land near the equator, a scenario that seems nearly impossible, unless the entire planet had been plunged into a deep freeze. So how does something like this happen? Earth is usually pretty good at balancing its temperature. When it gets warmer, certain feedback systems help cool things down. When it gets cooler, others help warm it up. But sometimes the balance tips too far in one direction. One possible trigger was the reduction of greenhouse gases like carbon dioxide. Volcanic activity might have slowed. Weathering of newly formed mountains could have drawn carbon dioxide out of the atmosphere. Even the placement of continents near the equator may have contributed, reflecting more sunlight back into space and lowering global temperatures. Once Earth began to cool, ice formed. And here's the tricky part. Ice is really good at reflecting sunlight. This is called the ice albedo feedback. Albedo is a measure of how much light a surface reflects. Ice and snow have a high albedo, which means they bounce a lot of sunlight back into space, preventing it from warming the planet. So as more ice formed, Earth absorbed less heat. Less heat meant more ice. And so this cycle continued, cold begetting colder, until glaciers had spread across much of the planet's surface. In this frozen world, life faced enormous challenges. Photosynthetic organisms near the surface of the ocean would have struggled, as sunlight was blocked by thick layers of ice. Temperatures plummeted, conditions became harsh and inhospitable, and yet somehow life survived. How did it manage such a feat? One possibility is that not all of the oceans were entirely frozen. There may have been patches of open water near the equator, so-called slush-ball Earth conditions, where life could still access sunlight and carry on photosynthesis. Another possibility is that life retreated to the warm comfort of hydrothermal vents, deep beneath the ocean, where heat and minerals flowed freely from the Earth's interior. Microbial life is extraordinarily resilient. Even today we find microbes in boiling acid pools, under Antarctic ice sheets, and inside rocks buried kilometres underground. So while Snowball Earth may have been a global deep freeze, it wasn't necessarily a mass extinction event. Life clung on, waiting patiently for the thaw. But how did the thaw actually happen? After all, once Earth was frozen and sunlight was being bounced back into space, what could possibly warm it up again? The answer, as it so often is in planetary science, lies in volcanoes. Even during a global ice age, volcanic activity doesn't stop. Deep within Earth, molten rock continues to churn and bubble. Volcanoes kept erupting, quietly belching carbon dioxide into the atmosphere. But with the oceans frozen and plants struggling, there were few natural systems to absorb that carbon dioxide. It began to build up. Over millions of years, this volcanic carbon dioxide created a thick greenhouse effect. The planet's icy surface, while reflective, could only hold off the accumulating heat for so long. Eventually, temperatures began to rise, glaciers melted, oceans re-emerged. The great ice sheets retreated, and Earth was once again transformed, this time from frozen wasteland to steamy greenhouse. This dramatic thaw likely happened quickly on a geological timescale, perhaps within tens of thousands of years, which is the blink of an eye compared to the hundreds of millions it took to freeze. As the ice melted, newly exposed land began to weather, drawing down the excess carbon dioxide and stabilizing the climate once again. Earth had found its balance, at least for a while, and with the melt came opportunity. The end of Snowball Earth wasn't just a relief to the planet, it may have been a gift to life itself. The dramatic environmental shifts may have spurred evolution. Nutrients flushed into the oceans from melting glaciers could have triggered massive algal blooms, fueling food chains and encouraging biological diversification. Indeed, shortly after the end of the Snowball Earth episodes, we start to see signs of more complex organisms in the fossil record. This includes the enigmatic Ediacaran biota, soft-bodied organisms that seem to mark a stepping stone between the microbial world and the explosion of animal life that would follow in the Cambrian period. In a strange way, Earth's brush with global ice may have helped prepare the stage for multicellular life. Harsh conditions forced organisms to adapt, cooperate, and innovate. When the thaw came, the survivors were ready to take advantage of a world brimming with possibility. It's a humbling reminder that even disaster can be a doorway, that sometimes, out of cold and silence, life finds its next chapter. So as you rest now, drifting between warmth and sleep, picture the Earth as it once was, silent, gleaming, and white. A frozen pearl spinning in the dark, its oceans locked beneath kilometers of ice. No trees, no flowers, just wind, snow, and the slow breath of a planet waiting to wake. Beneath the ice, life whispers, it endures, and when the thaw comes, it stretches, reaches, and begins again. The silence after the thaw must have been deafening. Imagine Earth slowly waking up after millions of years of icebound sleep. Glaciers melting, oceans stirring, rain falling again on land that hadn't seen the sky in eons. A planet previously locked in frozen stillness now humming faintly with life. And as the sun warmed the seas and the ice retreated, life began to do something it hadn't done before. Get loud in its own microscopic way. What followed was one of the most remarkable chapters in the history of life on Earth. A period of innovation, experimentation, and evolutionary fireworks. Scientists call it the Cambrian Explosion, and though the name suggests something sudden and perhaps even noisy, it was more like a slow-burning spark that lit the biological fuse. The Cambrian period began around 541 million years ago. Before this time, most life on Earth was microscopic. Single-celled organisms dominated the oceans, with the occasional multicellular blob tossed in for variety. But during the Cambrian, life began producing hard parts: shells, spines, plates, and exoskeletons. And with these protective structures came new forms, new strategies, and a much better chance of leaving behind fossils. The result? A sudden and dramatic increase in the diversity of visible life, preserved in stone for us to marvel at 500 million years later. It's worth pausing to appreciate just how big of a leap this was. For billions of years, Earth's oceans were mostly a soup of single-celled life. Then, almost as if someone turned on the evolutionary lights, we get a burst of complexity. Creatures with legs, eyes, jaws, and even nervous systems. It wasn't magic, of course. It was the result of long, slow evolution, meeting just the right conditions. Several factors likely contributed to this explosion of life. For one, oxygen levels in the oceans had finally reached a tipping point. After billions of years of oxygen build-up, the seas were now rich enough in this life-giving gas to support more active, energy-hungry organisms. More oxygen meant more fuel, and more fuel meant organisms could grow larger, move faster, and develop more complex structures. Another key ingredient was the appearance of predation. Before the Cambrian, most organisms floated passively, absorbed nutrients, or grazed gently on microbial mats. But once the first predator showed up, probably something small and toothy with a keen sense of direction, everything changed. Evolution got competitive. Prey evolved armor. Predators evolved better hunting tools. This evolutionary arms race spurred a frenzy of adaptation that produced a staggering variety of new body plans. And let's not forget the geology. Plate tectonics had shuffled Earth's continents around, creating new coastlines and shallow seas, perfect environments for life to flourish. Nutrients washed from the land into the oceans, feeding algae and creating rich, blooming food webs. The Earth was, in many ways, ready for a biological boom, and boom it did. One of the most famous fossil sites from this period is the Burgess Shale in the Canadian Rockies. Discovered in the early 20th century, it contains exquisitely preserved fossils of Cambrian organisms, many of which defy easy classification. There are creatures that look like a cross between a shrimp and a leaf blower. Others resemble walking pine cones with eyes. It's a menagerie of the strange and wonderful, an evolutionary workshop with all the tools scattered on the floor. Among the stars of the Cambrian seas was Trilobite, one of the first arthropods. These hard-shelled, segmented critters scuttled across the seafloor, sporting compound eyes and an impressive array of body armour. They were the cockroaches of the Cambrian, ubiquitous, tough, and endlessly adaptable. Trilobites would go on to dominate the oceans for hundreds of millions of years, evolving into thousands of different species. Another favourite is Anomalocaris, a creature whose name means abnormal shrimp. It was one of the earliest known apex predators, growing up to 3 feet long, a true giant in a sea of tiny things. With large compound eyes, a circular mouth full of spiny plates, and grasping limbs near its head, it likely terrorised the Cambrian reefs, vacuuming up soft-bodied prey like a roaming underwater Roomba with an attitude. Then there was Opabinia, a creature so strange that when paleontologists first presented it, the audience laughed, thinking it was a joke. Opabinia had 5 eyes perched on stalks and a long, flexible proboscis ending in a claw. It looked like something a child might dream up after eating too much cake. But it was real, and it represents the kind of evolutionary experimentation that made the Cambrian so remarkable. This period was also when the first recognisable ancestors of modern animal groups emerged. Early versions of mollusks, worms, echinoderms and chordates began to take shape. Chordates, by the way, are the group that would eventually include fish, birds, reptiles, mammals, and us. One early chordate was Picaia, a small eel-like creature with a notochord, the stiff rod that would later evolve into vertebral columns. In a quiet, wriggly sort of way, Picaia was one of our earliest known relatives, and perhaps that's what makes the Cambrian Explosion so extraordinary. It's not just a flurry of strange creatures with hard shells and spindly limbs. It's the moment our deep ancestors first appeared in the fossil record. The moment the tree of life grew a few new, crucial branches that would, many millions of years later, lead to eyes that could gaze at stars and hands that could build telescopes. But not every creature from the Cambrian made it to the modern era. Many of the wild, experimental body plans vanished as quickly as they arrived. Evolution is creative, but it's also ruthless. Only the forms best suited to their environment stuck around. Others, like evolutionary doodles, were erased by time. By the end of the Cambrian period, the world was a different place. The seafloor was crowded with burrowers, grazers and hunters. Plankton drifted through the upper waters. Coral-like organisms began building tiny reefs. The biosphere had grown louder, busier, more complex, and all of it was happening underwater. Dry land, for now, remained a barren and rocky silence, waiting for its turn. The Cambrian Explosion reminds us that evolution doesn't always move at a constant pace. Sometimes the right conditions, a mix of oxygen, nutrients, open niches, and a dash of competition, can light a fire under biology. And once lit, that fire can burn in dazzling, unpredictable directions. So tonight, as you drift into sleep, picture the Cambrian seas, clear, sunlit waters swirling with life, trilobites marching across the ocean floor, Anomalocaris drifting by like a prehistoric submarine, strange soft-bodied creatures undulating in the current, trying out limbs and eyes and nervous systems for the first time in Earth's long history. It was a world of endless possibility, a moment when life decided to take the plunge into complexity and never looked back. The sea had been good to life. For hundreds of millions of years, Earth's oceans were the cradle of all biology. They offered stability, protection, and an all-you-can-eat buffet of floating nutrients. But sooner or later, curiosity, or perhaps necessity, tends to get the better of even the most contented creatures. And so, sometime around 400 million years ago, life did something unthinkable. It climbed out of the water and stepped, rather clumsily, onto dry land. This chapter of Earth's history is often called the Great Migration, not because anyone packed bags or booked tickets, but because it marks one of the most significant relocations in the story of life. Organisms that had evolved entirely underwater began to explore a world without tides, waves, or buoyancy. It was a risky move, but a revolutionary one, because from that point onward, life would never be limited to the sea again. But let's not get ahead of ourselves. Before animals dared to set foot on land, plants led the way. The very first land plants likely evolved from green algae, simple aquatic organisms that had already mastered photosynthesis. Around 470 million years ago, some of these algae adapted to live at the edges of freshwater lakes and rivers, where they were occasionally exposed to the air. Over time, these pioneers evolved the structures needed to survive out of water: waxy coatings to prevent drying out, anchoring roots, and vessels to move water and nutrients internally. These early plants didn't look like today's forests. Picture low, mossy mats and small, spongy stems clinging to the damp soil. But they did something extraordinary. They began changing the very surface of the earth. Their roots broke up rock, creating soil. Their presence stabilized sediments. And most importantly, they pumped oxygen into the atmosphere while pulling carbon dioxide out. The land was, quite literally, being terraformed from the ground up. As plant life flourished, it set the stage for the next bold move: animals. But crawling onto land was no simple feat. Water provides buoyancy, which means most marine animals don't have to support their own weight. On land, gravity pulls with no mercy. Gills don't work in air, and skin dries out quickly. Any animal hoping to survive on land would need new tools, and evolution was up for the challenge. The first animal trailblazers were likely arthropods, a group that includes insects, spiders, and crustaceans. Some of these early arthropods, possibly ancestors of modern millipedes, scorpions, or springtails, were already equipped with tough exoskeletons that helped prevent dehydration. They had jointed legs for movement and rudimentary respiratory systems suited for breathing air. Fossilized tracks and body imprints suggest they were wandering onto shore as early as 430 million years ago. They probably weren't there for the view. The land offered untapped food sources, decay in plant matter for example, and no predators, at least not yet. It was a buffet with no line, and the arthropods took full advantage. Meanwhile, back in the water, fish were evolving too. The Devonian period, which began around 419 million years ago, is often called the Age of Fishes, and for good reason. This was a golden age for fishy innovation. Some evolved armoured plates, others developed strong jaws and sharp teeth. But a few extraordinary fish began experimenting with a radical idea: limbs. These fish belong to a group called the lobe-finned fishes. Unlike the ray-finned fish that dominate today's oceans, lobe-finned fishes had sturdy, fleshy fins supported by bone. One of these ancient fish, Tiktaalik, discovered in Arctic Canada, offers a perfect snapshot of this transition. It lived around 375 million years ago and had both fish-like and tetrapod-like features. It had gills and scales, but also flat, paddle-shaped fins with bones resembling wrists. Its eyes were on top of its head, perfect for peering out of shallow water. Tiktaalik wasn't exactly strolling through meadows, but it could likely pull itself up into mudflats or onto roots near the water's edge. It was a pioneer, an evolutionary bridge between swimming and walking. From these early amphibious fish evolved the first tetrapods, four-limbed vertebrates that could move and breathe on land. Over time, their fins became legs. Their gills were supplemented, then replaced by lungs. Their bodies adapted to support their weight outside of water. These early tetrapods probably returned to the water to lay eggs, much like modern amphibians, but their presence on land was unmistakable. Imagine it: a dim, mossy swamp with buzzing insects and low, fern-like plants. A lobe-finned fish wriggles up the muddy bank, eyes blinking in the sunlight, body heaving with effort. Every movement is a struggle, but also a triumph. For the first time, a vertebrate is breathing air. This wasn't a single event, it was a slow transformation, repeated in countless individuals over millions of years. But eventually, legs and lungs became the new standard, and life on land kept getting better. As plants grew taller and more complex, they created shaded environments, new food sources and microhabitats. forests began to spread, rich with invertebrates and shelter. The air, once thin and dry, thickened with oxygen and moisture. And through it all, animals followed, crawling, hopping, and eventually running through landscapes that just a few million years before had been completely lifeless. The move from water to land also marked the beginning of an explosion in biodiversity. New niches meant new opportunities. Creatures evolved to burrow in soil, climb plants, or glide between trees. Some grew scales to conserve moisture. Others developed better lungs, sharper senses, or complex limbs. The land, once barren, was now alive with movement. But this wasn't just a biological revolution. It also changed the Earth itself. Plants absorbed carbon dioxide, a major greenhouse gas, and released oxygen. Over millions of years, this helped cool the climate. Forests locked up carbon in wood and soil. Deep root systems altered the composition of rocks, influencing erosion and sedimentation. And as animals moved nutrients around, through grazing, burrowing, and yes, pooping, they began to shape ecosystems in entirely new ways. In short, the Great Migration wasn't just a matter of switching zip codes, it was the beginning of a whole new world. So as you lie here tonight, letting your thoughts drift like ancient spores on the wind, picture the first brave steps onto land. Imagine tiny arthropods skittering over damp moss. Picture a muddy fish pulling itself forward with half-formed limbs. Hear the hush of wind through primeval ferns, the hum of early insects, the heartbeat of a planet quietly cheering on its newest explorers. From water to land, from gills to lungs, life had taken a bold new path. And the journey was only just beginning. One of the most fascinating things about Earth's history is how each chapter builds on the last. From lifeless rock to microbial seas, from single cells to soft-bodied ocean explorers, and finally to the bold leap onto land, life has never been content to stay still. And now, with the land colonized and oxygen levels rising, Earth was ready for something big, something leafy, something loud. Welcome to the age of towering plants, buzzing insects, and creatures the size of coffee tables crawling through damp forests. Welcome to the Carboniferous Period, a time when Earth became a jungle playground for evolution's wildest ideas. The Carboniferous Period began roughly 359 million years ago and lasted for about 60 million years. It was a time of high oxygen, high humidity, and lush, sprawling forests, unlike anything the world had seen before. The name Carboniferous actually comes from the Latin for coal-bearing, because much of the coal we use today formed from the dense plant matter that flourished during this period. Let's start with the plants. The land was now dominated by vast swampy forests filled with giant ferns, towering horsetails, and club mosses that grew to the size of trees. These weren't modern seed plants just yet. No apples, no daisies, but they were big, green, and determined to soak up every bit of sunlight they could find. Some of these ancient trees grew more than 100 feet tall, with bark as thick as armour and shallow roots that twisted through muddy soil. These forests were dense and dark, full of humidity and filtered light. The air was rich with oxygen, so much so that it may have reached concentrations as high as 35%, compared to 21% today. That's an atmosphere ripe for wildfires, and also for giant bugs. Yes, insects took full advantage of the high oxygen environment, and they did it in style. This is the period when you'd find dragonflies with wingspans of over 2 feet, millipedes the size of a small dog, and enormous amphibians lounging in the swamp. It's as if nature decided to hold an evolutionary costume party and didn't enforce a dress code. The reason these creatures could grow so large comes down to their respiratory systems. Insects and similar invertebrates don't breathe the way mammals do. Instead of lungs, they use a network of tiny tubes called tracheae that deliver oxygen directly to their tissues. The larger the concentration of oxygen in the air, the more efficiently this system works, and during the Carboniferous, the air was like a supercharged oxygen smoothie. The the ground teemed with life. Giant centipede-like creatures called arthropleura crawled through the undergrowth. Amphibians resembling chunky salamanders and miniature crocodiles slithered through the waterlogged forest floor. Early reptiles began to appear as well, still small and primitive, but getting ready to conquer the land in their own way. But the real stars of the show were the plants. As they died, their remains didn't decompose quickly. The wet, oxygen-poor soils of the swampy forests slowed the breakdown of organic material. Instead of rotting, the plant matter piled up into thick, spongy layers called peat. Over millions of years, pressure from sediment built up on top of these layers, compressing them into coal. This is why we call it the Carboniferous Period, because it literally gave us the coal beds that powered the Industrial Revolution and still influence human history today. These massive plant accumulations also helped shape the atmosphere. Plants, as you might recall, absorb carbon dioxide during photosynthesis and release oxygen. With more plants than ever before, carbon dioxide levels dropped and oxygen levels rose. This created a cooling effect on the climate. Glaciers began to form near the South Pole, and by the end of the Carboniferous, the planet was entering another ice age. It's a reminder that life and climate are deeply connected, a fact that still holds true today. Let's take a quiet walk through a Carboniferous forest just for a moment. The ground is soft with peat. Thick ferns unfurl like green fans above your head. The air is damp, heavy with the smell of moss and decay. A dragonfly the size of a dinner plate buzzes past in a slow, graceful arc. Somewhere in the underbrush, a small amphibian plops into a murky stream, sending ripples through a world unchanged for millions of years. There's no bird song. Birds haven't evolved yet. No flowers either. No mammals. But there's life everywhere, tangled and humming and ancient. One of the most remarkable things to emerge from this period was the first true egg layers, early reptiles. Amphibians, for all their innovation, still had to return to water to lay their eggs. Their eggs were soft and jelly-like, requiring moisture to survive. Reptiles, on the other hand, evolved amniotic eggs, complete with protective shells and internal fluid, allowing them to reproduce away from water. This seemingly small development was a game-changer. It meant reptiles could move further inland, into drier habitats where amphibians couldn't follow. It laid the foundation for a whole new wave of terrestrial life, including eventually dinosaurs, birds, and mammals. By the end of the Carboniferous, Earth was shifting again. The supercontinent Pangaea was beginning to take shape as tectonic plates slowly merged landmasses together. The climate was cooling, the swamps were drying, and many of the vast coal forests began to disappear. Oxygen levels dropped. The giant insects faded. But their time in the sun, quite literally, had left a mark that still lingers in the seams of ancient rock. So tonight, as you settle into bed, imagine this world of giant ferns and buzzing titans, a humid, prehistoric greenhouse where every breath was rich and every leaf was lush. Picture the hush of ancient forests, the glimmer of light through a 100-foot canopy, and the slow march of amphibians dragging themselves through the mud in search of their next meal. The Carboniferous period was a time when the Earth itself was building a library of fossil fuels, storing energy from the sun in layers of ancient peat. It was a time of oxygen and overgrowth, of enormous insects and evolutionary firsts. A green world, thriving and wild, just before the next great turn in the story of life. Earth has a habit of reinventing itself, just when life seems to be hitting its stride, when forests stretch to the horizon and strange creatures are lounging in swamps. Something big, really big, tends to happen. And by big, we mean catastrophic. This chapter in Earth's story is about endings, not quiet, graceful fade-outs, but abrupt, world-altering, everything goes wrong kind of endings. Mass extinctions, reset buttons, the times when life was forced to start again from nearly zero. To be clear, extinction is a normal part of life on Earth. Species come and go all the time. In fact, scientists estimate that over 99% of all species that have ever lived are now extinct. But every so often, extinction arrives on a scale so massive, so devastating, that it leaves the entire planet transformed. These are the mass extinctions, the punctuation marks in Earth's long sentence of life. There have been 5 major mass extinctions in Earth's history, and we'll touch on several of them in this chapter. But let's begin with the biggest, the one that truly earned its dramatic nickname, the Great Dying. About 252 million years ago, during the final days of the Permian period, life on Earth was flourishing. Reptiles were evolving into a diverse range of shapes and sizes. Giant insects still buzzed through the forests. Coral reefs teemed with life. Then something went terribly wrong. In just a few million years, a blink of an eye in geological terms, about 96% of all marine species and 70% of terrestrial vertebrate species vanished. This was the Permian-Triassic extinction event, and it was the worst extinction in Earth's history. So, what happened? The leading theory points to massive volcanic activity in what is now Siberia. These eruptions weren't your average smoke and lava kind of deal. They were flood basalt eruptions, gigantic, long-lasting outpourings of lava that covered vast areas with molten rock. Over hundreds of thousands of years, these eruptions released enormous amounts of carbon dioxide, methane, and other greenhouse gases into the atmosphere. This created a runaway greenhouse effect. Temperatures soared, ocean chemistry changed, the seas became more acidic, and oxygen levels plummeted, creating so-called dead zones where nothing could survive. On land, ecosystems collapsed under the weight of heat and drought. Some scientists also believe that massive releases of methane from seafloor deposits may have accelerated the warming, tipping Earth's climate into a full-blown crisis. Imagine a world where the ocean turns stagnant and lifeless, where forests die back into dust, where scorching heat waves roll across the continents without end. That was Earth during the Great Dying. But even after this devastation, life persisted. A few hardy species clung on, small reptiles, burrowing creatures, some opportunistic marine animals. And from those survivors, evolution began its slow work once more. Over the next several million years, new ecosystems emerged. It was the beginning of the Mesozoic era, the age of dinosaurs. But before we get to the dinosaurs, let's step back and look at some of the other major extinction events that helped shape Earth's biological history. One of the earliest mass extinctions happened near the end of the Ordovician period, around 444 million years ago. At that time, life was mostly in the oceans, and it was doing pretty well. Corals, trilobites, and jawless fish swam through shallow seas. Then, a rapid drop in global temperatures triggered a massive ice age. Sea levels fell, habitats vanished, and many marine species were left stranded or frozen. It's thought that up to 85% of marine species disappeared in this event. Then there was the late Devonian extinction, roughly 375 million years ago. This one wasn't a single sharp event, but rather a series of drawn-out blows over several million years. It disproportionately affected marine life, particularly reef-building organisms and early fish. The causes are still debated. It might have involved climate change, ocean anoxia, a fancy term for no oxygen, or even the spread of land plants, which altered the chemistry of soil and rivers, affecting the oceans downstream. The fourth major extinction came at the end of the Triassic period, around 200 million years ago. By this time, the first dinosaurs had appeared, but they weren't yet the rulers of Earth. That changed after the extinction, which cleared out many of their early competitors. The culprit? Once again, massive volcanic activity, this time in what would become the Atlantic Ocean, as the supercontinent Pangaea began to break apart. Carbon dioxide levels surged, temperatures rose, and ecosystems collapsed. With the field cleared, dinosaurs rose to dominance and strutted their stuff across the Jurassic and Cretaceous landscapes. And that brings us to the fifth, and perhaps most famous, mass extinction of them all, the one that ended the age of the dinosaurs. About 66 million years ago, at the end of the Cretaceous period, Earth was home to a dazzling array of creatures. Dinosaurs ruled the land, pterosaurs soared through the skies, and massive marine reptiles patrolled the oceans. Then, in the cosmic equivalent of a very bad day, a chunk of rock roughly 6 miles wide slammed into what is now the Yucatan Peninsula in Mexico. The impact released more energy than 1 billion nuclear bombs. It triggered global wildfires, mega tsunamis, and earthquakes. Dust and aerosols shot into the atmosphere, blocking sunlight and plunging the planet into darkness. Photosynthesis stopped. Food chains collapsed. The age of dinosaurs came to an abrupt and fiery end. Roughly 75% of all species went extinct in that event, including all non-avian dinosaurs. But once again, some life made it through. Small mammals, crocodilians, certain birds. From those survivors, new life flourished, and eventually the mammals took centre stage. It's easy to think of these extinction events as only destructive, but they're also strangely creative. Each one cleared the ecological slate, opening space for new forms of life to evolve. After the Great Dying, reptiles diversified into new shapes. After the Devonian extinction, early land plants and amphibians spread into new territories. After the dinosaurs, mammals bloomed into the astonishing variety we see today. That's the strange duality of extinction. It is both an end and a beginning, a closing door and a new path. Life, though battered and broken, always finds a way to return, to adapt, and to thrive again. Tonight, as you lie quietly in your own warm little corner of this ancient planet, imagine the world as it once was. Lush forests teeming with creatures long gone, oceans filled with animals we'll never meet, skies filled with wings that no longer beat. Picture the sudden stillness that follows disaster, the silence after a long rain, the hush that settles when the world holds its breath. Then imagine the stirrings that follow, the first sprout of green in burned soil, the flutter of a tiny creature peeking out from shelter, the slow, persistent return of life. Mass extinctions may shape the course of evolution, but they never stop it. They remind us of how fragile our world can be, but also of how strong life truly is. And as Earth continues to turn, slowly and steadily beneath the stars, the story continues. Always changing, always evolving, always beginning again. The stage was cleared. The old rulers had fallen. After the End-Triassic extinction, much of Earth's biological landscape was wide open. Habitats vacant, ecosystems dismantled, and evolutionary opportunities waiting to be seized. And into that vacuum stepped one of the most iconic and captivating groups of creatures ever to walk the Earth, the dinosaurs. This was their moment. Dinosaurs weren't born into greatness. They didn't immediately stomp around in glory, roaring across the land with jaws wide open and tails dragging behind. Their story began more quietly, during the late Triassic period, roughly 230 million years ago, with small, nimble, mostly bipedal reptiles, some no larger than a dog. These early dinosaurs shared the Earth with many other reptilian groups, including early crocodile relatives, mammal-like synapsids, and various now extinct oddities. But when the Triassic extinction swept away many of their competitors, the dinosaurs were poised to take the spotlight. They diversified rapidly, evolving into a stunning array of forms, each more specialized than the last. And so began the Mesozoic era's middle chapter, the Jurassic period, a golden age for dinosaurs. Let's start by setting the scene. The Jurassic period, which began about 201 million years ago, was warm, humid and lush. There were no polar ice caps, sea levels were higher, and vast shallow seas lapped against the edges of the continents. Pangaea, the supercontinent, had begun to break apart, slowly creating the arrangement of land masses we recognize today. This continental drift created coastlines, islands, and climate variations that helped drive evolution. The land was covered in dense forests of conifers, cycads, and ferns. Flowering plants had not yet evolved, so the landscape looked different from the flowery fields and grassy meadows we're used to. Instead, it was more like a prehistoric pine jungle, buzzing with insects, crawling with reptiles, and shadowed by giants. And when we say giants, we mean it. This was the age of the sauropods, some of the largest animals to ever walk the earth. These long-necked, long-tailed herbivores were true marvels of biology. Take Brachiosaurus, for example. It could grow over 80 feet long and stand as tall as a 4-story building, with a neck that stretched high into the tree canopy to munch on foliage most other creatures couldn't reach. Another titan, Diplodocus, stretched even longer. Some estimates suggest lengths of over 90 feet. Its tail may have been used like a whip to fend off predators, and its sheer size made it nearly untouchable by anything other than the most determined carnivores. But sauropods weren't the only stars of the Jurassic. This was also the age of the stegosaurs, armoured herbivores with distinctive plates running down their spines and spiked tails, referred to scientifically as thagomisers, a term that started as a joke in a cartoon, but is now used by paleontologists with a straight face. Predators, too, were evolving rapidly. Allosaurus was among the top carnivores of the Jurassic, a powerful, agile hunter with sharp claws and a mouth full of serrated teeth. Though smaller than the later Tyrannosaurus rex, Allosaurus was no less formidable. It hunted in what are now the plains and deserts of North America, likely stalking herds of sauropods and picking off the young, sick, or unwary. Meanwhile, high in the canopy and flitting through the underbrush were early ancestors of birds. That's right. Birds are not just related to dinosaurs. They are dinosaurs. Specifically, they evolved from a group of small feathered theropods, the same broader group that includes the likes of Velociraptor and Tyrannosaurus. One of the earliest and most famous bird-like dinosaurs is Archaeopteryx. Living about 150 million years ago, it had feathers, wings, and hollow bones like a bird, but also teeth, a long bony tail, and clawed fingers like a reptile. It was a perfect blend of old and new, and a key piece of evidence in understanding how flight evolved. Back on the ground, the Mesozoic menu was rich with variety. Dinosaurs had taken over every corner of the ecosystem. There were horned dinosaurs, crested ones with clubs for tails, others with elaborate frills and beaks. Some dinosaurs travelled in herds, others were solitary. Some built nests and cared for their young, while others likely left their eggs to hatch in the sun. By the time the Cretaceous period began, around 145 million years ago, dinosaurs were more diverse than ever. The Cretaceous would be their final act, but also their most dazzling. Flowering plants appeared for the first time, adding splashes of colour and scent to the landscape. New kinds of insects evolved to pollinate them, which in turn created new food chains and feeding strategies. The Earth was blooming. This period introduced some of the most famous dinosaurs of all: Triceratops with its 3 horns and bony frill, Ankylosaurus armoured like a tank with a massive club at the end of its tail, and of course Tyrannosaurus rex, perhaps the most iconic predator in Earth's history. Tyrannosaurus wasn't just big, it was a masterclass in predatory design. It stood over 12 feet tall at the hips, stretched over 40 feet long, and had teeth the size of bananas. Despite its famously tiny arms, it had an enormous bite force capable of crushing bone. For a long time, paleontologists debated whether T-Rex was a fearsome hunter or a lumbering scavenger. Now, evidence suggests it was likely both, opportunistic and powerful, and not one to turn down an easy meal. But while dinosaurs ruled the land, the skies were being explored by another group of ancient reptiles, the pterosaurs. These winged creatures were not dinosaurs, but close relatives. They came in many sizes, from small sparrow-like flyers to Quetzalcoatlus, with a wingspan that may have stretched over 30 feet, as wide as a small airplane. And below the surface of the oceans, marine reptiles like Mosasaurus, Plesiosaurus and Ichthyosaurus hunted fish and squid in ecosystems entirely separate from their land-dwelling cousins. These weren't dinosaurs either, but they were just as incredible, ruling their own watery kingdoms with flippers, teeth, and speed. All the while, mammals were there too, small, furry, nocturnal, and mostly staying out of the way. They nibbled seeds, darted through undergrowth, and slowly, quietly, prepared for their own chapter in Earth's history. But for now, the world belonged to the dinosaurs. So what made them so successful? A few key traits help explain it. First, they were incredibly adaptable. Dinosaurs evolved to fill a huge range of ecological roles, from tiny insect eaters to massive leaf munchers to apex predators. Second, they likely had high metabolisms, especially the theropods, which allowed for more active lifestyles. And third, many species laid eggs and may have exhibited parental care, which improved the survival rate of their young. Some scientists also believe that many dinosaurs were warm-blooded, or at least had metabolic rates somewhere between cold-blooded reptiles and warm-blooded mammals. This would have given them an edge in maintaining activity and colonizing different climates. The presence of feathers in many species suggests insulation and temperature control, traits we associate more with birds than with scaly reptiles. For over 160 million years, dinosaurs were the dominant terrestrial vertebrates. They survived changes in sea level, shifting continents, volcanic eruptions, and climate fluctuations. They were resilient, innovative, and deeply embedded in every part of the Mesozoic world. But nothing lasts forever. Their reign would eventually come to an end, not through slow decline, but in an instant. A catastrophic asteroid impact, as we'll explore later, brought the Mesozoic era to a close. Still, for over 100 million years, dinosaurs defined what life on land looked like. And remarkably, their legacy lives on. Every robin, crow, eagle, and penguin is a living dinosaur, a feathered echo of a world that once thundered with footsteps and filled the skies with leathery wings. So tonight, as you settle under your blanket, close your eyes and picture a world of giants. A land where enormous herds of sauropods lumber through fern-filled valleys, where raptors dart through ancient forests, and where tiny feathered creatures hop from branch to branch, the earliest ancestors of the birds singing outside your window today. The age of dinosaurs was a time of majesty, mystery, and motion, an age that reminds us that life, when given the time, the space, and the sunlight, will always find new and extraordinary ways to fill the earth. It began with a streak of light in the sky, a flash, a roar, and then silence. Not the gentle hush of a sleeping forest, or the stillness of a windless night, but the kind of silence that follows devastation. A silence broken only by the crackle of global wildfires, the crash of towering waves, and the slow settling of ash that would blanket the earth for years. This was the end of the Cretaceous period, and with it the end of the age of dinosaurs. 66 million years ago, Earth was a vibrant, thriving world. Dinosaurs ruled the land in all their variety. Horned, feathered, armoured, and bipedal. Flying reptiles soared through the skies. Giant marine predators hunted in warm, shallow seas. The continents, though not yet in their modern positions, were starting to resemble the world we know today. Flowering plants bloomed across plains and forests. Insects buzzed between blossoms. Early mammals, still small and scurrying, nibbled seeds and crept through the underbrush. It was a world filled with sound, colour, and life. And then everything changed. The cause of the extinction that ended the Cretaceous, and with it, about 75% of all species on Earth, is now widely agreed upon: a massive asteroid impact. The evidence for this comes from a thin, worldwide layer of clay rich in iridium, a rare element on Earth's surface but common in asteroids. This layer, found in rocks dated precisely to the time of the extinction, forms a boundary in the geological record known as the KP boundary. But the smoking gun is a crater. Buried beneath the Yucatan Peninsula in Mexico is the Chicxulub crater, a scar over 180 kilometres wide, formed by an object estimated to be about 10 kilometres across. That's about the size of a city, travelling faster than a bullet, slamming into Earth with the force of billions of nuclear bombs. The immediate effects of the impact were catastrophic. The explosion vaporised everything for hundreds of kilometres around. The surrounding ocean boiled. Shockwaves rippled through the crust. A towering tsunami surged out in all directions, inundating coastlines across the globe. Molten rock was thrown into the atmosphere where it rained down as glass-like beads. The heat from this falling debris may have ignited wildfires on a global scale, turning forests into ash and sending plumes of smoke into the sky. And then came the darkness. Dust, soot, and sulfuric aerosols filled the atmosphere, blocking sunlight for months or even years. Photosynthesis ground to a halt. Plants died. The herbivores that depended on them starved. The predators that depended on the herbivores starved too. Temperatures dropped. Acid rain fell. The climate shifted abruptly into chaos. In this rapidly collapsing world, the great non-avian dinosaurs, those iconic titans of Earth's past, vanished. Tyrannosaurs, Triceratops, Hadrosaurs, Ankylosaurs, gone. The flying reptiles, the pterosaurs, gone. The giant marine reptiles that had dominated the seas, gone. But not everything perished. Some animals made it through. The reasons why are still being studied, but certain traits seem to have helped. Small body size, burrowing habits, diet flexibility, the ability to go dormant or hibernate. Among the survivors were the ancestors of modern birds, tiny, feathered theropods that had already begun to adapt to flight, nesting behaviour, and perhaps even caring for their young. Their smaller size, rapid reproduction, and potential ability to find food more easily may have given them a critical edge. Mammals, too, survived. Not the big ones, they didn't exist yet, but small, furry, warm-blooded creatures that had spent the Mesozoic era living quietly in the shadows. Many were insectivores or omnivores, able to eat a wide range of foods. Some likely took shelter underground or in crevices, where they were insulated from the heat and cold. Crocodilians also survived, as did turtles, snakes, frogs, and various fish and invertebrates. The extinction was severe, but it wasn't total, and in its aftermath, life began to recover, slowly, tentatively, but with the resilience that defines evolution. In the years immediately following the impact, Earth was a very different place. The skies were dark and cold, the forests were gone, ecosystems had collapsed. But over time, the dust settled, the sunlight returned, and the ashes gave way to green. Plants regrew, insects returned, and with them came the small creatures that had endured, the survivors, the adaptable, the lucky. In this new world, the absence of dinosaurs left open niches. With the giants gone, there was space to grow, to spread, to explore. And that's exactly what the mammals did. But that's a story for another chapter. The end Cretaceous extinction is often romanticised, perhaps because of how iconic the dinosaurs have become, or because we can point to a single dramatic cause, a rock from space, a moment of impact, the end of an era. But in truth, it's a sobering reminder of how fragile life on Earth can be, of how even the most dominant, widespread and successful groups can vanish almost overnight when the conditions change. Yet it's also a story of resilience, because life didn't end. It endured, it adapted, and it filled the empty spaces left behind with new forms, new strategies, and new possibilities. As you rest tonight, perhaps you can imagine that moment, the flash in the sky, the rumble beneath the ground, the long silence that followed, and then the first green sprout rising from the ash, the first bird singing into a quiet dawn, the first small mammal creeping through the undergrowth, unaware that it was standing at the beginning of a new world. The dinosaurs may have disappeared from the land, but they didn't vanish entirely. Every robin, every eagle, every hummingbird fluttering outside your window carries their legacy. They are the living echoes of a past we can only glimpse in stone, Extinction may end a chapter, but Earth always keeps writing. The asteroid had fallen, the skies had darkened, the giants were gone. But in the stillness that followed the end of the Cretaceous, something remarkable was about to unfold. From the ashes of extinction came a quiet stirring, a twitch of a whisker, the crunch of an insect in the dark, the first padded footfalls of a new kind of animal emerging into the light. The age of the dinosaurs had ended, but the age of mammals was just beginning. For most of the Mesozoic era, mammals had been the underdogs. While dinosaurs roamed the land, flew through the skies and swam in the seas, mammals kept to the shadows. They were small, nocturnal, and often insectivorous, with sharp senses and clever brains. They had fur to stay warm and, in many cases, live births to give their offspring a better start in life. They had evolved during the late Triassic period, around 220 million years ago, and had quietly diversified throughout the Jurassic and Cretaceous. But they had never taken centre stage, until now. With the dinosaurs gone, ecosystems were wide open. No more towering sauropods to munch the foliage, no more carnivorous giants to rule the food chain. Mammals seized the opportunity like an actor stepping onto an empty stage, blinking in the spotlight. In the early days of the Paleocene epoch, just after the extinction event, mammals were still small, mostly no larger than cats or rabbits. But they were fast, adaptable, and full of evolutionary potential. Some were already beginning to explore new ecological roles. There were burrowers and climbers, swimmers and gliders, omnivores and herbivores. The world was slowly rewilding itself, and mammals were at the forefront. Over the next 10 million years, mammal species rapidly diversified in a process known as adaptive radiation. With so many ecological niches left vacant by the extinction, mammals evolved to fill them. Some became specialized herbivores, grazing on the fresh explosion of flowering plants that now dominated the landscape. Others became predators, developing sharp teeth, powerful limbs, and new hunting strategies. One of the most significant changes during this time wasn't just size or diet, it was intelligence. Mammals began to evolve larger brains relative to their body size. Complex social behaviours, problem-solving abilities, and stronger bonds between parent and offspring started to appear. By the time the Eocene epoch rolled around, about 56 million years ago, mammals were running the show. Forests had spread across much of the Earth. The climate was warm and stable, and the land teemed with a bizarre and beautiful array of new mammals. There were strange hoofed creatures with long legs and small heads, prowling carnivores that resembled modern cats and dogs, and enormous herbivores with tusks, trunks, and padded feet. Some early whales began as four-legged shore-dwellers before taking the plunge back into the sea, eventually becoming the fully aquatic giants we know today. It's during this time that the ancestors of many modern mammal groups began to appear. Primitive primates swung from trees, early elephants stomped through tropical forests, tiny protobats fluttered awkwardly between tree branches. Everything was trying something new. One fascinating group from this time was the condylarths, a diverse collection of hoofed mammals that were the ancestors of many modern herbivores. From these came the perissodactyls, odd-toed ungulates like horses, rhinos, and tapirs, as well as the artiodactyls, even-toed ungulates like deer, pigs, and eventually whales. Meanwhile, in the northern forests, small primates were beginning to evolve better depth perception, grasping hands and larger brains, traits that would prove very useful when leaping between branches or eventually pondering abstract thoughts. By the Oligocene epoch, around 34 million years ago, mammals had become larger, more specialized, and more widespread. Grasses began to spread across the continents, replacing forests in some areas, and giving rise to new grazing animals like early horses and antelope. These grasslands were also perfect hunting grounds for fast-running predators, some of which, like the hyenodon, looked like giant hyenas with bone-crushing jaws. As the Miocene epoch arrived, about 23 million years ago, many of the familiar animal families we recognise today were already roaming the planet. Elephants were growing larger, their tusks curving into iconic shapes. Saber-toothed cats prowled the plains. Early apes were swinging through the trees of Africa and Asia. The continents continued to drift toward their modern positions. Land bridges allowed animals to migrate and mix. In South America, isolated for millions of years, marsupials and giant flightless birds evolved into top predators and herbivores. In North America and Eurasia, placental mammals like bears, horses and wolves competed and evolved. Then, around 7 million years ago, a new kind of ape began to emerge in Africa, one that would eventually walk upright, fashion tools, and gaze up at the stars. But we'll come back to that story a little later. Let's take a quiet stroll through a world in transition. The dinosaurs are gone. The forests are alive again. A woolly mammoth plods across a grassy plain, steam curling from its breath in the cold air. Saber-toothed cats crouch in the shadows, their long fangs glinting in the twilight. High above, an eagle circles lazily, scanning the earth for movement. The earth is familiar now, recognizable even. You might spot an ancestor of your pet dog trotting through the undergrowth. A distant relative of a cow grazes in the field. A monkey swings by, chattering cheerfully, unaware of the millions of years that will pass before one of its descendants builds a telescope. Mammals didn't just survive, they thrived. And in doing so, they reshaped the biosphere. They became pollinators, seed dispersers, predators, and prey. They travelled from pole to pole across deserts, over mountains, through forests and swamps. And while none of them had any idea what was coming next, evolution was quietly, steadily preparing for one of its boldest experiments yet, intelligence on a scale never seen before. But for now, the mammals were content simply to roam, eat, sleep, and raise their young in a world that for the first time belonged entirely to them. So as you drift off tonight, picture a warm forest at dawn. A troop of lemur-like primates stretches and yawns as the sunlight filters through the trees. Nearby, a curious creature with padded feet and twitching ears sniffs the breeze, alert to the sound of distant footsteps. This is a world between worlds, post-dinosaur, pre-human, a world full of fur and teeth and wide, watchful eyes, a world shaped by the quiet persistence of mammals who, through luck, cleverness, and the sheer will to survive, stepped into the light and never looked back. Because life, as always, finds a way. The long, slow rise of mammals set the stage. Forests had grown thick with leaves and chatter. Herds thundered across grasslands. Paws padded, hooves clattered, wings flapped, and eyes blinked curiously beneath the sun. But somewhere in the midst of all this familiar life, something unfamiliar was stirring, something upright, tool-wielding, thoughtful. It wasn't sudden, evolution rarely is. But over the course of millions of years, something extraordinary began to unfold, the emergence of humans. To understand how we got here, how one species came to build cities, paint cave walls, send robots to Mars and wonder about its own origins, we need to go back about 7 million years to the forests and savannas of Africa. This was where the first hominins appeared. Not yet human, not quite ape, but something in between. These early ancestors were likely small, bipedal primates that still spent a good deal of time in trees. One of the earliest known is Sahelanthropus chidensis, a species that lived around 7 million years ago. Its skull suggests a mix of traits: small brain, but a face more human than chimpanzee, and perhaps an upright posture. Over time, more species emerged. There was Australopithecus afarensis, which lived around 3.5 million years ago and walked fully upright, leaving behind footprints preserved in volcanic ash at Litoli in modern-day Tanzania. These creatures were small, with long arms and curved fingers, still climbers, but now committed to life on 2 legs. Why bipedalism? It's a mystery with many possible answers. Walking upright may have allowed early hominins to travel more efficiently across open landscapes. It freed up their hands to carry food, tools, or infants. It may have even helped with thermoregulation, less of the body exposed to the blazing African sun. As these early hominins walked, watched, and wandered, their brains began to grow. Enter Homo habilis, roughly 2.5 million years ago. Often called the handyman, this species is known for its use of simple stone tools, sharp flakes chipped from rocks, likely used to cut meat or crack bones. It wasn't much by modern standards, but it marked a turning point. Technology had entered the picture. From Homo habilis came Homo erectus, a tall, long-legged species that truly began to stretch its range. These early humans were remarkably successful. They walked out of Africa and into Asia and Europe. They made fire. They lived in groups. They hunted, scavenged, and survived in a wide range of environments. Their skulls were still small compared to ours, but their faces had begun to flatten, and their brains were larger than any hominin before them. Homo erectus persisted for nearly 2 million years, a staggering length of time, and their success laid the foundation for what came next. Then, around 300,000 years ago, something truly extraordinary happened. In Africa, a new species emerged, Homo sapiens, United States. At first glance, we were not that different from our cousins. We used tools, walked upright, cared for our young. But something was different. Our brains were even larger and more complex. Our vocal structures allowed for more nuanced communication. And our culture, our ability to learn, teach, imitate, and imagine, began to explode. But we weren't alone. For a long time, other human species shared the planet with us. There were the Neanderthals, Homo neanderthalensis, living in Europe and parts of Western Asia. Stocky, strong, and intelligent, they made sophisticated tools, wore clothing, and buried their dead. There were also the Denisovans, known from only a few bones and genetic traces, but clearly important. In Southeast Asia, tiny Homo floresiensis, the so-called hobbits, inhabited the island of Flores. In the Philippines, another small hominin species lived, Homo luzonensis. For tens of thousands of years, the Earth was home to multiple human species at once. We were not yet alone, but then, one by one, they disappeared. Whether due to climate changes, competition, interbreeding, or a combination of factors, Homo sapiens became the last human standing. By around 50,000 years ago, our ancestors were spreading across the globe in earnest. They crossed deserts and mountains, followed coastlines, and braved unknown seas. Along the way, they left behind traces, stone tools, cave paintings, carved figurines, and eventually language. It's hard to overstate the significance of this period. It was a cognitive revolution. Our ancestors began to use symbols. They created art. They developed complex rituals. They built shelters, shaped tools with purpose, and formed intricate social bonds. The world became more than just a place to survive. It became a place to belong, to wonder, and to create. In Europe, humans painted vivid images of animals on cave walls at sites like Lascaux and Chauvet. In Africa, they engraved geometric patterns into ochre blocks. They left behind necklaces, figurines, and ceremonial burials. These were not just survival tools, these were signs of a growing mind, one capable of abstract thought, empathy, and imagination. And then came agriculture. Around 12,000 years ago, in a few fertile pockets of the world, humans began to cultivate plants and domesticate animals. It was a quiet revolution, but one that changed everything. No longer entirely dependent on hunting and gathering, people began to settle. Villages formed, populations grew, societies took root. From these early agricultural communities came the first cities, then kingdoms, then civilizations. Writing emerged, trade networks spread, empires rose and fell, science, art, and philosophy blossomed, and all of it, the pyramids, the printing press, the moon landing, was built on the shoulders of millions of years of quiet, steady evolution. Yet through all of this change, we remain deeply connected to our ancient past. Our hands are the hands of toolmakers, our eyes shaped by the needs of our primate ancestors. Our social nature, our storytelling, our empathy. They are not new inventions, but ancient traits refined over time. Even now, as we navigate digital worlds and artificial intelligence, we carry within us the echoes of early forests, stone tools, and long-forgotten fires. So tonight, as you drift off to sleep, imagine those early humans huddled together under a canopy of stars. One of them is shaping a flint blade. Another is telling a story. A third stares quietly into the flames, dreaming of something more. They do not yet know the future. They don't know about skyscrapers, satellites, or the whispering hum of electric lights. But they carry within them the potential for all of it. The spark is already there. From ancient apes to astronauts, the journey of Homo sapiens has been extraordinary. We are not separate from the story of life on Earth. We are its latest chapter, and perhaps, if we are wise, not the final one. Because the story continues. It always does. Our journey across Earth's history has taken us from molten rock to molecules, from microbes to megafauna, from soft-bodied creatures drifting in Cambrian seas to upright apes carving tools beneath the African sun. Life has risen, fallen, and risen again, again and again, sculpted by time, pressure, fire, ice, and chance. But now, in this final chapter of Earth's long history before the present day, we find ourselves standing at a curious moment, a moment where the storyteller is also the story, where one species has gained the power to shape the world not just through biology, but through ideas. Welcome to the modern age and the dawn of humans as a geological force. The last 12,000 years or so represent the Holocene epoch, a brief and unusually stable period in Earth's history. Before that, for nearly 2.5 million years, our planet was gripped by cycles of glaciation during the Pleistocene epoch. These were the Ice Ages, when massive glaciers advanced and retreated, carving valleys and shifting coastlines. Humans lived through all of it. Early Homo sapiens weathered bitter cold and changing climates by using fire, crafting clothing, building shelters, and relying on each other. They hunted mammoths, mastodons, and giant sloths. They painted on cave walls and sang songs we'll never hear. But when the last great ice sheets began to melt, around 12,000 years ago, things changed. The climate stabilized, rain patterns shifted, rivers flowed more predictably, and our ancestors began doing something unprecedented. They stayed put. This was the agricultural revolution, and it reshaped everything. In places like the Fertile Crescent, the Yangtze River Valley, the Andes, and Mesoamerica, people domesticated plants and animals. Wheat, barley, rice, maize, yams, goats, sheep, cattle. Permanent settlements emerged. Villages became towns. Towns became cities. Populations grew. Societies became more complex. Governments formed. Religions spread. Writing systems were invented to keep track of crops, trade, and stories. And with this web of human activity came something new: history. Civilizations rose in Mesopotamia, Egypt, the Indus Valley, and China. Each one contributed something remarkable: irrigation, astronomy, architecture, metallurgy, law. Humanity was no longer just adapting to the environment. We were adapting the environment to suit us. For a long time, human influence on the planet was significant, but local. Fields were cleared, forests were cut down, rivers were diverted. But Earth, on the whole, continued to operate as it always had. Volcanoes erupted, ice caps waxed and waned, species evolved. Then came the Industrial Revolution, beginning around the late 1700s. This was another turning point, perhaps the most profound since the invention of agriculture. Fueled by coal, steam, and eventually oil and gas, machines replaced manual labour. Cities swelled. Railways and steamships connected continents. Factories churned out goods. Electricity lit up the night. The internal combustion engine roared to life. And with this rapid technological growth came a massive rise in resource use. Forests were cleared not for survival, but for industry. Mountains were mined. Rivers were dammed. Landscapes were transformed at speeds Earth had never experienced. The 20th century accelerated this trend even further. Oil and gas fueled global economies. Highways stretched across nations. Air travel shrunk the planet. Plastics, concrete, and synthetic chemicals altered the environment in ways nature had never seen before. By the mid-20th century, Earth had entered a new epoch, one some scientists now call the Anthropocene, the age of humans. We became a geological force. Think about that. A single species, emerging only a few 100,000 years ago, now moves more sediment than all the world's rivers. Our buildings and roads weigh more than all living trees. We have changed the chemistry of the oceans, the composition of the atmosphere, the albedo of the poles, and the balance of life across nearly every continent. Our footprint is everywhere. From space, you can see the lights of our cities, the checkerboard of our farmland, and the scars of our mining operations. Of course, this power comes with consequences. Climate change, driven largely by the burning of fossil fuels, is altering Earth's systems in complex and sometimes dangerous ways. Global temperatures are rising, ice sheets are melting, sea levels are creeping upward, weather patterns are shifting, coral reefs are bleaching, species are migrating or disappearing. We are also in the midst of what some call the sixth mass extinction, a rapid loss of biodiversity not driven by asteroid impact or supervolcanoes, but by habitat destruction, pollution, and overexploitation. It's a sobering picture, but it's also incomplete without acknowledging something else, something uniquely human. Awareness. We know we're doing this. For the first time in Earth's history, a species is capable of not just shaping the planet, but understanding what that means. We can measure carbon in the atmosphere, track wildlife populations, study ocean currents, and model future climates. We can talk, reflect, argue, and try to change course, and we are. Around the world, people are rethinking energy, food, water, and waste. They are planting forests, protecting species, inventing cleaner technologies, and working to create a more sustainable way of living. It's not simple, it's not fast, but it's happening. Because while we are capable of harm, we are also capable of wonder, of empathy, of invention, of care. We are still the descendants of toolmakers, firekeepers, and story sharers, still shaped by evolution, even as we shape the world around us. So where do we go from here? That's a question Earth can't answer on its own. For the first time in 4.5 billion years, one of the planet's life forms is aware of the path it walks and can choose where it goes next. We might continue on our current trajectory, transforming Earth in ways that make it less hospitable, not just for other species, but for ourselves. Or we might use our knowledge and creativity to build a future where nature and technology coexist in balance. The choice isn't one moment, it's 1,000 little moments. Decisions made every day, by individuals and communities and countries. And as daunting as it may seem, it's also hopeful. Because the story of Earth has always been one of change, of adaptation, of resilience. We are not outside that story, we are not a footnote or an exception. We are a chapter, one that is still being written. So tonight, as you lie back and breathe softly, think of the planet beneath you, not just as a rock floating in space, but as a living history book, its pages written in stone, ice, bone, and breath. You are part of that story, a character in the grand, ongoing narrative of Earth. And though we don't yet know the ending, we do know this. The Earth endures, and life, despite everything, keeps finding a way. And so, here we are, at the end of our quiet journey through time, from stardust to soil, from single cells to symphonies, from molten chaos to conscious minds. We've followed the long, winding path that led from Earth's fiery birth to the gentle turning of our own present day. Along the way, we've seen continents drift, mountains rise, oceans churn, and life unfold in dazzling, unexpected forms. We've watched mass extinctions wipe the slate clean, and we've seen the survivors, tiny, stubborn, miraculous, start again each time. We've met the trilobites, the dinosaurs, the giant ferns, the mammoths, and at last ourselves. You, listening now, are a product of all that. Your body, your thoughts, your breath. Every part of you is stitched into this grand, ancient tapestry. Your Stardust story and the latest chapter of a 4.5 billion year adventure. So before you drift off, let's circle back, gently, to where we began. Where in the world are you listening from? A quiet city? A countryside far from noise? Somewhere warm and breezy? Or curled up under a heavy winter quilt? What time is it for you? Is it just past midnight, 2 in the morning? Are you finishing a long day or beginning a short rest? And perhaps most curiously, did you make it to the end awake? Or did Earth's story, with all its gentle layers and distant echoes, lull you into sleep somewhere along the way? If you're still here, thank you for listening. If you enjoyed this journey through deep time, please consider leaving a like and subscribing to The Sleepy Scientist. It helps us grow our little corner of curiosity and calm, and brings more quiet wonder to sleepy minds all over the world. Wherever you are, whenever you are, may your dreams be full of ancient forests, drifting continents, and the quiet hum of life continuing on. Good night, fellow traveller, and remember, you're part of Earth's story now too.